Welcome to AP Podcast 10.8. This is on vapor pressure. And vapor pressure is simply the pressure above the liquid at equilibrium. Now, we haven't really talked about this equilibrium term yet, but just imagine, I'll go over it in just a second, just imagine it's where the amount of vapor that's evaporating is the same as the amount that's condensing. So let's look at a couple terms. First, we've got vaporization, and that's simply from changing from the liquid to a gas at the boiling point. And of course, how does this occur? Well, you've got to overcome the intermolecular forces, right? And then evaporation. Okay, evaporation is the change of a liquid to a gas below the boiling point. And if you've ever sat a glass on the table and come back later in the day, you probably notice that the liquid is at a different level. And think about this. This is happening all on its own. So this is occurring, and it's occurring without any heating. So somehow there's enough molecules in the beaker right here, or the Erlenmeyer flask, that can overcome those attractive forces and still evaporate. And that's important. Now we're going to see another delta H term, and this is just the heat of vaporization, somewhat known as the enthalpy of vaporization. And of course we can calculate that out, but the standard is it's the energy required to vaporize 1 mole at 1 atmosphere. Again, some standard condition things. So we've got evaporation and vaporization. Now, as I just had mentioned, vaporization requires some heat, all right? So therefore, it is an endothermic process. You want to recall that sometimes people, when you talk about, is this reaction endothermic or exothermic, and when they think of heating things up, they often think of it as an exothermic reaction. But remember, if you're heating things up, something is absorbing that heat, and so that's an endothermic process. And when those molecules overcome the intermolecular forces, that's when they leave the beaker or the flask or whatever. Now, what's important about vaporization and vapor pressure is this is the reason we have a nice cool earth. All right, all that water is absorbing a ton of energy, and therefore when it's absorbing that energy, we get evaporation, and that makes some clouds, and that eventually causes condensation, and the whole water cycle occurs. But if you don't have a big heat sink like all the water we have on this planet, then you don't have something that can absorb all that energy. And then more importantly, this is why we sweat. All right, think about what's going on when we're sweating. We're adding heat from our skin into we're adding heat to the skin to the outside. Now on the outside we have that water, right? Now those water molecules are sitting there. They're absorbing the heat from our skin, and then they're going into the vapor state. So they're absorbing heat. And as you guys know, when you touch something cool, it feels cool because heat is leaving you. It's not that you're feeling the cold, it's that you're feeling the heat leave you. So when heat leaves my skin to go into the sweat, that causes the sweat to go into vapor, and then you feel cool. So that's why we sweat, all because of this vaporization. Now let's talk a little more about dynamic equilibrium. And all that is imagine if we had a closed container. Here's my Erlenmeyer flask with a nice closed container. And these molecules in here, some are overcoming the intermolecular forces and they're escaping. But after a while, it gets so concentrated up in this area that some of those molecules will actually condense and go back down. And so what happens is this occurs over and over and over till right here at this point somewhere you get the same amount going up as you do going down. And that is called equilibrium. And so when you get those two points happening, the rate of vaporization equals the rate of condensation, that's when we reach that dynamic equilibrium. Now, vapor pressure, just a little bit more stuff, is when we have a liquid that has a very high vapor pressure, we call those volatile liquids. And a volatile liquid, some of the ones that you know of from everyday life would be like rubbing alcohol. Okay, if you open up a container of isopropyl alcohol in your bathroom, you can smell it. Okay, how about this? Gasoline. If you've ever pumped your gas, you know there are vapors pumping out there. Why is that? Well, the vapor pressure of those gases is pretty high. And the reason it is because those intermolecular forces are lower than something like water, and so they're giving off their vapor. Okay? Now, what would happen if I heated those up? You know exactly what would happen if I would heat those up. Okay? The vapor pressure would increase. So if I go back to this thing right here, and I were to put a flame underneath here, here's my awesome flame. Look at that. Okay? I put a flame there, and I'm causing heat to go up there. What do you suppose is going to happen to those molecules in the liquid? The kinetic energy is going to increase. They're going to move around faster, causing more molecules to go up into the vapor phase. So that's important. And then vapor pressure decreases with intermolecular forces. So what that means, if you think back to when we first introduced intermolecular forces, big molecules, right? If you have bigger molecules, they're more polarizable. They're more polarizable, right? What does that mean? That means they have a larger LDF, London dispersion forces, and therefore they'll have a better, think of it as holding power on the molecules, so they can't escape. And then if you have molecules that are more polar, okay, if you've got more polar attractive forces, well, that's going to cause that, that's going to cause that vapor pressure to go up. All right, so those two things have a big effect with vapor pressure: the increase in temperature and the decrease in intermolecular forces. So I've got a couple graphs I want you to look at. So imagine temperature 1, and I've got this temperature. You know, just for the heck of it, let's just say it's 50 degrees Celsius. Okay, and at this point, you can see how many molecules you have, and here's the kinetic energy. The kinetic energy is increasing. At this temperature, you only have a certain amount of molecules here that can escape, that can go into that vapor phase. So it's sitting on a counter, and about that many can overcome. All right? Well, let's go to our second temperature. Now let's say this temperature is going to be, I don't know, let's say 100. Let's say it's 100 degrees Celsius. Right? So at T2, look at how much bigger this area is. And this is something that's been experimentally determined, and you can even determine it easily just by watching something. I mean, you put a pot on the stove, and you have it on low. All right? Well, you know some particles are going to evaporate. Let it sit for however long you want. And then turn the stove up to full blast, and then let it sit for the same amount of time. Promise you the water level is going to go down. So temperature causes those molecules to have enough energy to escape and go into the vapor phase. Okay, so vapor pressure, really, really important thing. All right, so there you go. We'll spend a little more time with this in class. See you next time.